Gases. I love gases. This is probably one of my favorite chapters. I like stoichiometry, but I like gases a lot too. So, gases are funny things because usually we can't see them, right? And yet they're very real, and they can cause a great deal of damage, or they can be used for good. If you think about a champagne bottle, there's a lot of gas pressure that is built up into it, and when you release that cork, it often goes flying, right? You see that a lot on TV shows and stuff. Sometimes it hits somebody in the face. But what causes that to go flying off? It's gas pressure. So we're gonna learn about this. So we have to understand some things about gases. Gases are composed of particles. They could be atoms or molecules that are moving around very quickly in their containers. The particles move in straight lines until they run into something. They may run into the wall of the container. They may run into another gas particle. When they run into things, they bounce off. And so there's a couple different ways that I picture gas molecules. They act a little bit like billiard balls. If you've taken physics, you know about elastic and inelastic collisions. Gas particles have elastic collisions, which means that when they run into something, they don't lose any energy, they just bounce off. I think even a better picture of gas particles is that ancient video game, that original video game, Pong. You guys at least heard of Pong? You know what it was? So you had this little screen, and it was green on black is how they used to be. And you had a paddle down here. This was like the original Atari kind of deal. That's crazy. Yeah. And so you had this line. They called it a paddle. It was just a line. And all you could do was move it right and left. And there was this blip. And the blip acted like a gas particle. The blip would move in a straight line until it ran into something, the wall or the paddle, and then it would bounce off, following the laws of physics. Angle of incidence equals angle of reflection, and it would bounce off, and you had to move your paddle so that it didn't hit the bottom of the screen. And sometimes you could get your paddle in just the right place where it would get into a square, not really a loop, but it would just keep bouncing. And that's when you could go to the bathroom, right? Because you couldn't save things and you couldn't pause things in those days. But that's a really ugly picture now, so I'm going to erase it. You get the idea. That's what gas particles do. They move in a straight line, and they're moving relatively quickly, and they just keep going until they run into something. Because they're not traveling through anything. They are the stuff that they're traveling through. If we were able to take a snapshot of the particles of a gas, we would see that there is a tremendous amount of empty space between the gas particles. So just like a ball exerts a force when it bounces against a wall, if anyone's ever thrown a ball at you and hit you, you recognize there's a force there. That hurt, right? So a ball bouncing off a wall exerts a force, and when these gas particles bounce off a surface, they also exert a force when they collide. The force is related to the mass of the particle, which is very small, and their speed, which is, relatively high. But the individual force of each gas particle hitting is teeny, teeny, tiny. But there's a lot of them, and they hit the surfaces a lot, and so it adds up. The result of many of these molecular collisions is what we call pressure. Pressure is force per unit area. It's the amount of force divided over the area. And we're not going to do calculations with that, but that helps us to understand some of the gas laws. So the gas pressure is a result of this constant movement of the gas particles and their collisions with the surfaces around them. The amount of that pressure is going to depend on several factors. How many gas particles are in the given volume? If you have a lot of gas particles, you're going to have more collisions than if you have a few. It's also going to depend on how big the container is. If you've got a really big container, there will be fewer collisions. And it also depends on the average speed of the gas particles. So if you think about people in a room, if you have 10 people or 50 people in a room, it's obvious that 50 people walking around, let's say they're walking around blindfolded, so they're just going to walk in a straight line till they bump into someone or something. There's going to be a lot more collisions if you have 50 people versus 10 people. If you take those 50 people in a small room or a large room, which one's going to have more collisions? The small room, right? If the people are running instead of walking, there's going to be more collisions, right?